So, let's talk about generative adversarial networks, or GANs. You've probably seen what they can do. They're this incredible duo of neural networks that basically battle each other into creating stunningly realistic images from, well, nothing. But here's the catch. What happens when all that creativity is completely random? I mean, what if we want to give the AI specific instructions and have it create exactly what we're thinking of? Well, that's the challenge we're going to tackle today. How do we teach this brilliant but kind of wild AI to become a master artist that actually takes requests?
So here's our game plan. We're going to start with the limits of a standard AI artist, the chaos. Then we'll introduce the simple command that finally tamed it, this CGAN. After that, we'll level up and tackle a much tougher challenge with a really clever round-trip trick called CycleGAN. And to wrap it all up, we'll look at how these incredible tools are already changing the world around us.
All right, so let's set the stage with the main problem. A standard GAN, for all its power, is like a brilliant artist who just paints whatever they want. It can create an absolute masterpiece, but you can't actually ask it for anything specific. You can't say, hey, paint me a portrait of my dog, or give me a landscape, but make it winter. Its creativity is just completely untamed.
And this really gets to the heart of the matter. This is the big question that pushed the whole field forward. We've got this amazing generator that takes in a bunch of random noise and spits out these incredible images. So how do we get in there? How do we take control of the AI's canvas and tell it exactly what we want it to create?
Well, the first big breakthrough that really cracked this problem was the Conditional GAN, or CGAN for short. And honestly, the name kind of gives it away. It's a GAN that works based on a certain condition that we get to provide. This is our way of finally handing the artist a set of instructions.
The idea behind the CGAN is actually pretty simple, which is what makes it so brilliant. We're not throwing out the old architecture. We're just giving it a little hint. Along with all that random noise it normally gets, we feed it an extra piece of info, a condition. And that condition is the command we've been looking for to steer the generator's output.
And this slide just lays it out perfectly. Look at the difference. On the left, a standard GAN just gets a scoop of random noise. But on the right, the CGANs generator gets that same noise plus a label. That one tiny addition, that label, is the command. It could be a category, a word, anything that gives the AI a little bit of context for what it's supposed to be making.
Okay, now this diagram shows you how the whole system works. Check it out. The generator on the left doesn't just get noise anymore, it also gets a specific label. So right away, it knows its job isn't just to make any image, but to make an image that matches that label. But here's the really clever part. The discriminator, the critic, also gets the label. So now it has two jobs. First, is this image realistic? And second, does this image actually match the label it was supposed to have?
Let's just walk through that real quick. So step 1, we give the generator its noise and a specific label, like let's say blonde hair. Then step 2, the generator does its best to create a face that has blonde hair. But step 3, that's the critical part. The discriminator looks at the image and the label and it asks two questions. Is this a believable face? And does it actually have blonde hair? So if the generator makes a perfect face but with brown hair, the discriminator says nope and rejects it. It's not just a reality check anymore. It's a strict supervisor, forcing the generator to follow the instructions.
To make this super concrete, just imagine we're telling it about hair color. We could use a simple little code, a vector. Maybe 1, 0 means not blonde hair, and 0, 1 means blonde hair. So by feeding that 0, 1 vector into the generator with the noise, we're literally telling it, point blank, generate a face and make sure it has blonde hair. It's that direct.
Now, CGANs are awesome, but they do have one big catch. They need paired data. To teach an AI to turn sketches into photos, you need tons of examples of the exact same thing as both a sketch and a photo. But what happens when you can't get that? What if you have, say, 1,000 photos of horses and 1,000 photos of zebras, but not one single picture of a horse with its matching zebra version? This is what's called the unpaired image-to-image translation problem, and it's a really tough nut to crack. How do you teach a machine to translate the style of one thing, like a photograph, to another, like a Monet painting, when Monet obviously never painted the photos you have on your camera roll? How does it learn the very idea of zebra-ness and figure out how to apply it to the body of a horse?
The answer to this is a ridiculously cool model called CycleGAN, and it solves this whole problem of unpaired data not by trying to find direct matches, but by using this super clever idea, a round-trip trick.
The core concept here is something called cycle consistency, and the best way to think about it is with language. If you translate a sentence from English to, say, French, and then you translate that French sentence back into English, you should end up with something pretty close to what you started with, right? Well, CycleGAN applies that exact same logic, but to pictures.
So let's break this down, starting with what's called the forward cycle. We actually have two generators now. Generator G is learning how to turn horses into zebras. We give it a real horse, let's call it X, and it spits out a fake zebra. Then, right away, we give that fake zebra to our second generator, F, and its job is the exact opposite. Turn zebras back into horses. The final output is our reconstructed horse. That's the first half of our round trip.
And here's the key. This is all happening in both directions at the same time. While that's going on, we're also running the backward cycle. We take a real zebra, Y, and give it to generator F to make a fake horse. Then we feed that fake horse right back to generator G to try and reconstruct the original zebra. By learning both of these translations at once, the model has no choice but to find a real, meaningful connection between the two sets of images. So how does it know if it's doing a good job? That's where this crucial measurement comes in. It's called the cycle consistency loss. The model basically just measures the difference between the original horse and the one it got back at the end, and the original zebra and the one it got back. The entire goal of training is to get that loss, that difference, as close to zero as possible. By forcing the final image to look just like the starting one, the model can't really cheat. It has to learn a proper translation, because it knows it's going to be tested on the trip back.
Okay, so now that we get the genius mechanics behind CycleGAN, let's check out some of the absolutely incredible things it lets us do. Because this isn't just some academic idea, it has some seriously powerful real-world uses.
Thanks to this really clever design, CycleGAN has become this amazing tool for all kinds of tasks, both creative and practical. I'm talking about turning a simple doodle into a photorealistic image, changing the seasons in a photo from summer to winter, or even creating brand new data to help train other AI models.
And here is a fantastic example: style transfer. So on the left, you've got a normal photograph. On the right, that same scene has been completely reimagined in the style of a Monet painting. I mean, look at the brushstrokes, the colors. The AI never saw these two specific images side by side. It just learned the essence of what makes a Monet painting and what makes a photograph, and it figured out how to translate between them. It's just incredible.
And it's not just for art. Here's a great example of what we call domain adaptation. The model was just given a bunch of summer photos and a separate bunch of winter photos. And now it can take the summer scene on the left and just so convincingly turn it into winter. And notice it's not just splashing white paint everywhere, right? It's smart. It adds snow to the ground, to the branches. It makes the light feel colder. It has actually learned the rules of what makes a scene feel wintry. And you know, beyond all these cool visual tricks, CycleGAN has some really practical uses. Like, imagine training a robot in a perfect computer simulation. CycleGAN can help bridge that gap, helping the robot adapt what it learned in that clean simulation to our messy, unpredictable real world. It's also an amazing tool for data augmentation. If you don't have enough pictures of something to train an AI, CycleGAN can help you create more realistic examples, which makes your other models way better.
So, as we've seen, this whole journey with GANs is really a story about gaining more control and sophistication. We went from the totally wild, random creativity of a standard GAN to getting its specific commands with CGANs, and finally to solving that really tough puzzle of unpaired translation with the beautiful logic of CycleGAN.
We've managed to give AI the ability to follow our commands and even translate entire artistic styles. It's not really just a creator anymore. It's more like a collaborator. So the big question we're left with is this: what's the next frontier for all this digital creativity? What's the next great challenge we're going to teach these amazing machines to solve?